Right, let's just recap quickly what we did last time. Last time we did the first two stages in the evolution of stars, the nebula and the main sequence star. And the point we got to was the main sequence star, which is a stable star. All right, as you know, the sun stays pretty much as it is, burning away quite happily. It's going to carry on doing that for an awfully long time. It's been doing it for an awfully long time in the past. It's clearly a very stable object, okay? Now, we saw with the nebula that gravity is in control. It's just making the nebula get smaller and smaller. So, as we saw last time, the balance comes from the fact that at the centre of the star, it's got to this important temperature of about 10 million degrees C, okay? Temperature which scientists at the moment on the Earth are struggling to maintain for doing nuclear fusion on the Earth. The stars manage it quite happily. Gravity just keeps squashing and squashing, and the temperature and the pressure and the density at the centre go up and up and up. And eventually they'll hit this point. This reaction, H plus H, turning into helium. So hydrogen nuclei squeezed into helium releases a huge amount of energy. And here's the strange bit. That energy has to push its way out. As we talked about last time, that's a very strange idea of light actually having to push its way out. But in the centre of a star, that's what happens. And it's the light and the infrared and the X-rays and the ultraviolet and all that stuff produced in the core of the star by nuclear fusion has to push its way out, and that creates what we call radiation pressure. Okay? So the little seesaw idea, I think, is a nice way to work through this section. In the main sequence star, we have this very stable situation. Okay? It is very stable. It's like a marble in the bottom of a teacup rather than a marble sitting on top of an upturned teacup. It's a very stable kind of stable. If you can imagine going up to a star, putting your rubber gloves on and squeezing it. Imagine I got this star that's quite happily that size and I squeezed it. What would I do to the temperature and the pressure at the centre? What would that do to the amount of fusion? And what would that do to the radiation pressure? Which would push it back where it was. Let's suppose I went up to a star and stretched it, made it bigger than it wanted to be. What would happen to temperature and pressure in the middle? Go down, and so the amount of radiation pressure would go. So who would win? Go back. Do you see? So even if, like, a giant army of comets all smashed into the sun or something, that's just ridiculous, because obviously they're just infinitesimally small compared to the sun. But imagine something really massive hit the sun. It's a fairly stable kind of thing, all right? It's that kind of like a marble in the bottom of a teacup. If you push it to the side, it will just settle itself back down, all right? And big topic we're not going to go into, obviously the sun does vary ever so slightly in its size and its light output and things like that. And we know that's linked to climate change on the Earth. And at the moment we're trying to unpuzzle, aren't we, the link between human activity and... But natural variation in the sun is responsible for things like, things like ice ages and stuff. Okay? Now, very important stage coming up. Radiation pressure and gravity. Which one needs fuel?
Radiation pressure.
Yeah, here's the problem. Gravity's never going to run out. As far as we can see, due to the work of a chap called Albert Einstein, we believe gravity is something fundamental to do with space and time. If you have a universe that has 3 dimensions of space and 1 dimension of time, and you put heavy things in it, then what's going to happen is you'll get gravity, all right? It doesn't have an engine. It doesn't need like a little fuel tank to make the gravity go. Unlike radiation pressure, which of course requires hydrogen nuclei. Yeah? Eventually, the radiation pressure is going to run out. Okay? So stage 2, which in the life of a star, I think like the adult stage, is the vast majority of your life. If, like Lemmy from Motorhead, in fact, you live for exactly 70 years, the biblical 70 years and 10. How much of that life do you live as an adult? How much as a child? Well, the majority of your life, you maybe go a bit bonkers in old age and you crawl around in your nappies when you're little, but fundamentally the big chunk of your life is as an adult. So think of it like the adult stage of a star, all right? Most of the life of a star, it lives as a main sequence star, but eventually, while gravity just goes on, radiation pressure is going to run out because the star is going to run out of hydrogen, okay? So there will come a point where this nice little stable seesaw can't continue. Okay? The good news for the sun is it's not coming for an awfully long time, 4,500 million years or whatever. It's not going to happen for simply ages and ages. The sun is roughly halfway through, we think. It's about halfway through its life. Very big stars, much bigger stars than the sun, obviously have much more hydrogen fuel because they form from a bigger nebula. It's as simple as that. So they will last, compared to the sun, Longer's a good answer, but you know me well enough now to know that would be the wrong answer, won't it? Thank you for that. Big stars last much less time. Really, really big stars. The blue one in Orion, if I can find it. Clicky thing.
Is it because it's burning fuel?
That's it. I mean, they are just the big fuel tank stars, aren't they? So if a bigger tank goes quickly, it's because it burns through it more quickly. The blue star in Orion, there's Betelgeuse up there. The blue star in Orion, Rigel, is a blue supergiant. It formed out of a much, much bigger nebula than the Sun did. It's much bigger, it's got a lot more hydrogen. Well, let's see if we can work out this puzzle, because Rigel is actually going to last much less time. You want to be glad you're not on a planet orbiting Rigel, because the amount of time there is for the planet to cool, life to form, get sploshed by a meteor, start again. Are you with me? The time for that on a star, on a planet orbiting a blue supergiant, is going to be a bit tight. You're going to struggle to get life on planets like this. So we think life is unlikely to evolve on planets around very, very big stars because they don't last very long. Okay? Reason for that, let's imagine a star twice the size of the Sun. Okay? It is a simple idea. You've got a fuel tank with a certain amount of fuel in, and you nosh away at it at a certain rate, and that's that. If you've got this much fuel, you consume it at this rate, you're going to last for this amount of time. Okay? Take a star twice the size of the Sun. How many times more fuel has it got than the Sun? 2. So you've got twice as much fuel. All right, so think of a fuel tank twice as big. Just draw a bit better. You've got twice as much fuel. Okay? How many times more gravity is there?
2.
Keep going.
16.
You've got twice as much gravity, and twice as much gravity. 2, 2, and 2. How many dimensions are there in space? 3. 2 times 2 times 2? It's 8. So there's going to be 8 times as much gravity. So if a star like this is going to do this sort of balance, what's the problem is, it's got 8 times the gravity. How many times more radiation pressure will it need? 8. So how many times more quickly must it nosh through the hydrogen? Now think about it. You're chugging along, the car next to you has got twice as much fuel, but it eats it 8 times quicker. Who's going to live longer?
You.
How many times? Work out.
4.
4, isn't it? So this star will actually, the Sun would last 4 times longer. A star twice as big as the Sun would last 4 times longer. All right? And Rigel, if you look it up, is many, many times, thousands of times bigger than the Sun. And that means its lifetime is not tens of thousands of millions of years. It's much, much shorter. Almost to the point where evolution of light probably isn't going to happen. Okay? So depending on the size of the star, big ones go quickly. Small stars take much longer. Okay? But for whatever star, for whatever reason, eventually you're going to come to a point where the radiation pressure is going to pack up. All right? These two things are in balance, but eventually, one day, the radiation pressure is going to fade away. Think of the seesaw. What's your prediction about the size of the star? If the radiation pressure starts to lose the battle?
It's going to get smaller.
The size of the star gets smaller.
It will, won't it? Because it's gravity that's going to win, and gravity requires no fuel. Which is the only tricky bit in this, really. Stage 3 in the life of a star is called red giant. So here's the tricky bit. Common sense and my excellent seesaw idea suggest the star's going to get smaller. But actually, the next stage in the life of a star is called a red giant. Okay? Is there a good red giant? I often think the constellation Orion is like pretty much the whole of stellar evolution in one constellation. Right? You've got main secret stars, you've got very large main secret stars, and here, Betelgeuse is a red star. It's called a red giant star. Okay? You can't really see them with your eyes. Your eyes don't really see colour at night. But anyway, red giant is the next stage. Very confusing because, of course, if the radiation pressure packs up, gravity's going to win. Well, gravity's only going one way, and it's going to make the thing smaller, surely. So we've got to puzzle out what on earth's going on with a red giant. Now, what happens in a red giant star? Well, it's a bit tricky because you're expecting the star to get smaller. Okay? One of the best explanations I've ever heard, for me, is the fact the star splits in two. In a main sequence star, the core of the star and the outer layers, the bit that you see, are in good contact. There's stuff made in the core of the sun, it wriggles out through the star and helps to support it against gravity, and then zooms off to the Earth. Okay? The core of the star, where the energy is made, and the outer layers, where it's radiated away, are in good contact. Okay? What happens in a red giant star is the two things kind of part company. Now, if you were thinking, this is bonkers, if you've got two things pushing like that, gravity pushing in, radiation pressure pushing out, surely if gravity's going to win, the star will get smaller. Well, in one sense, you're absolutely right. The core of the star does indeed get smaller. Okay? But that's not the bit of the star that we see. The outer layers get much, much bigger, massively bigger. When the sun becomes a red giant, Mercury, Venus, and the Earth will be inside it. All right? Mars will be the first planet in the solar system. All right? So in a red giant star, the outer layers, okay, and the core of the star start to do separate things. All right? And that's how come basic physics says the star's got to get smaller. Well, that's right. The core of the star, the energy-making part, does get smaller. But we don't see that. We see, that's what this diagram's trying to show you, not very well, is the core's getting smaller, but the outer layers get bigger, massively bigger. Now, let's see if we can work out what's going on. Okay, here's the star, here's the core, all right, it's happily shining away, it's producing radiation pressure which is beaming off to Earth, there we are, okay. Now, there will come a day when the sun has fused all its hydrogen. To give you an idea of how big the sun is, have you ever seen those posters with all the planets on, and sometimes at the very bottom they put the edge of the sun in? The sun fuses 4 million tonnes of hydrogen every second, and it's going to last for 10,000 million years odd. That'll give you an idea of how big the sun is. But there will come a day, even for a fairly long-lived star like the sun, where it runs out of hydrogen. What's the core of the sun going to be made of by that time? It's going to be made mostly of helium. Think about it. The reaction going on in the centre of the sun at the moment, well, it's not always obvious from looking at the sky. What's going to happen at the moment is hydrogen is being turned into helium. Not being lost, it's not disappearing. It's being rearranged, is the word I like to use. It's being rearranged into not little hydrogens, but little pairs called helium. Okay? Now the problem is, if you want to do this reaction, and you're full of helium, that's a bit of a problem. Obviously, if you run out of fuel, you can't do the reaction anymore. So there will come a day, obviously, when gravity doesn't get any weaker. Gravity's pulling in. The radiation pressure will start to splutter, all right? It will start to struggle to produce any kind of energy because it's really draining the bottom of the fuel tank. It's running out of any hydrogen to fuse. Well, go back to the seesaw. If the radiation pressure starts to fail, what's going to happen to the size of the star? Yeah. The core does get smaller. The core does get smaller. All right, the basic physics we were talking about earlier on, if this one packs up, gravity will win and it will start to get a bit smaller. What's that going to do to the temperature at the centre? Yeah. As gravity pushes in harder, it's going to push the temperature up to something like, let's say, 13 million degrees. Now, to fuse hydrogen, you only need a temperature of about 10 million degrees. And if you try and fuse helium at 10 million degrees, it doesn't work. But as the temperature goes up, as the radiation pressure fails, gravity pushes in, and so the centre of the star gets smaller and smaller, the temperature in the middle goes up, eventually you reach a point, I'm not sure if that's the exact right one, but something like that, where helium, beryllium, number 4 on the periodic table, okay, the little heliums that you have can start to be fused together to make number 4 on the periodic table, beryllium, okay. If you ever looked in chemistry and gazed at the periodic table and wondered where they will come from, about half of the answer is they're made in stars. All right, this is how you get helium, basically. A little bit of helium before it present at the start of the universe, but fundamentally, it's made in stars. The sun currently is turning hydrogen into helium, but when it starts to run out of hydrogen, it will get smaller, and that means it'll get hotter, and eventually it'll reach a temperature where it can do that. It can fuse helium, and that will release some more energy, And a nice way to think about this, can you imagine the sun starts to run out of hydrogen, the core gets a bit smaller, and then suddenly it realises it can start to do helium fusion. The energy switches back on again. So the fusion switches back on, the radiation pressure comes back on, and the outer layers, it's almost like a little mini explosion. The outer layers get thrown right out. Okay? And that's what creates what we call the red giant star. Okay? If you're thinking it's run out of fuel, it must get smaller, you're right. The business department of the star, the core of the star, which in an ordinary star is linked closely to the outer layers of the star, but in a red giant they're starting to go different ways. And what happens is, as the radiation pressure switches back on, it pushes out the outer layers. They then get much further from the centre, so what's going to happen to their temperature out here? And instead of being a nice cheery yellowy orange colour, they cool to a... Do you get the word now? Red giant. All right. It does seem a bit odd, but hopefully now you can see why the star becomes a red giant. The business department gets smaller and starts to fuse more exotic things, and the outer layer becomes a red giant. However, can you see the problem? What's going to happen a bit later on? Now, eventually, this is going to happen again. Because turning the helium that the sun's making at the moment, when it's made all of the hydrogen into helium, it'll start turning the helium into beryllium. But that won't take very long. All right? The reason why it won't take very long, if you started off with 100 hydrogens, how many heliums can you make from 100 hydrogens? How many berylliums can you make? You've only got half the fuel. All right? The problem with these later stages in the life of a star's main sequence is it's only got half the fuel. All right? And think about the size of the core. Is gravity going to be stronger now or weaker? If the star gets smaller, it's stronger, isn't it? So unfortunately, it's double bad news. You've got twice, only half the fuel. So you can imagine yourself in the engine room of the star, and they say, well, let's do it again. Let's burn all that beryllium you just made. I'm afraid you've only got half the fuel, and are you going to need more radiation pressure to be stable or less? You're going to need more, aren't you? Because to be a stable star, you need to balance your gravity with your radiation pressure. Gravity's now stronger, I'm afraid, because you've still got, the star still weighs the same. All those little nuclei that made the helium, that made the beryllium, they're still there. That's why rearrangement is a good word for the margin. You're rearranging them. All that mass is still there, but it's not now the size of the sun. It's now a good deal smaller, isn't it? Okay? And that's basically why you're going to need more radiation pressure. So if you're in the engine room of the star, they say, oh, by the way, in fact, it's triple bad news. You're going to have to produce more energy because the star is now smaller. Gravity's pushing in harder. We need more radiation pressure. You've only got half the fuel, and even worse bad news, I can show it like this. Hydrogen plus hydrogen makes helium, gives you a lot of energy. Helium plus helium makes beryllium, gives you quite a lot of energy, but not as much. So can you imagine that? You're shoveling the heliums and shoveling the hydrogens. In the days of hydrogen fusion, it was great. Gravity wasn't too strong, so you didn't need to produce too much radiation pressure. You got plenty of hydrogen, you had 100, and each time you fused a hydrogen, you got loads of energy. Let's go to here, stage 3 if you like, beryllium plus beryllium. It's oxygen, isn't it? It's oxygen, all right? This is a nightmare. You've got to produce more energy. You've now got a quarter of the fuel. You've only got 25 of these. And each time you do fusion now, you don't get as much energy. So pretty quickly, the beryllium's going to run out, and then you start doing, and so on. Okay? A really, really good way of thinking about this, just lose my main sequence star. A really good way of thinking about the life of a star is spiral. The first time round the spiral takes 10,000 million years, and you do nice and easy. Loads of fuel, an excellent reaction, and you don't need to produce massive amounts of radiation pressure because the gravity isn't too strong. Second time round, it gets, I beg your pardon, second time round, it gets a bit more tricky. The star's smaller, so you need more energy. You haven't got as much fuel, and the reaction doesn't produce as much energy. Third time round, it gets even worse, all right? And this is basically what happens as the star gets smaller and smaller, okay? This is why, as I said, it goes main sequence. Stage 3 is red giant, okay? But eventually you lose these outer layers, okay? You lose these outer layers. The outer layers of the red giant star will eventually just cool away and become gas again, all right? They'll just form another nebula, all right? Eventually you're just left with the middle of the star, the business part of the star, and you keep going round and round this spiral, okay? Down here, beryllium plus beryllium makes oxygen is a real nightmare. You need to produce even more energy because the star's even smaller. You've got a quarter of the fuel, and each reaction doesn't produce anything like the amount of energy that it used to. And so if this lasts 10,000 million years, these will last progressively less and less, okay? You might be thinking, I see, chemistry is just an offshoot of astronomy, and it is, and we'll discuss that another time, but I can see now why the universe around me isn't just hydrogen. When the universe did the Big Bang thing, it's almost 90-odd% hydrogen. But you look at the world around you, it's got helium, lithium, beryllium, carbon, nitrogen, oxygen. All these other ones are being formed as you go along, okay? However, there's a problem, and a nice way to think about it is to think about the spiral stopping at iron, all right? There's a problem with forming all the elements this way. And the problem comes, I can't work it out, if you've got a periodic table and a boring moment in a chemistry lesson, you can work it out. But eventually, you keep doing this, you're eventually going to get up to iron, roughly in the middle of the periodic table. Okay? Now, there'll come a time when your star is now basically just made of iron. It's fused everything into iron. And you might think, well, I can guess what's going to happen, Mr. King. It's going to be iron plus iron equals, no, don't know what it is. Something plus a little tiny bit of energy. Well, the answer is that doesn't happen. Nuclear fusion has to stop at iron. Fusion works because when you take two nuclei of light elements and put them together to make a heavier one, that process releases energy, all right? But that, as you get closer and closer to iron, the amount of energy gets less and less. And when you get to iron, it reaches 0. So if you get two iron nuclei and you squeeze them together to make something bigger, you don't just get not much energy like you do from these ones. You get not even nothing. They won't do it unless you put energy in. So how much radiation pressure is this going to generate to hold up the star? Nothing. All right? And we've now entered, effectively, stage 4 of the life of a star, which is called the white dwarf. It's like a red giant, but the outer layers are floated off. That's a bit rubbish, but it's sort of the idea. So if you're looking at your red giant on the screen there, eventually those outer layers are just going to drift off into space. The core of the star, the business energy generating parts, going to get smaller and smaller, and eventually you're left with... That's quite nice. It's a montage, obviously. But you get the idea. To get the idea, main sequence star, red giant drawn way too small. If that's the main sequence star, if that's the main sequence star, the red giant star will be many times bigger. But then eventually, you're left with the core. All right? Main sequence, red giant, white dwarf. If you were thinking, hang on a minute, gravity's been pushing harder and harder all the time, and it's mucking about all sorts of funny reactions, but fundamentally the star's got to get smaller. You're right. There's the core of the main sequence star, there's the core of the red giant star, and there's the core, you see. Look at the seesaw again. Basically, gravity's winning. And the centre of the star, the core of the star, is getting smaller. All right? Now, we don't actually see that. Ironically, we actually see a stage where the star seems to get bigger, but that's just the outer layers being pushed out. All right? Core of the star gets smaller, basic physics, because of this. Okay? Which leads us to, and that's the start at the end there, stage 4 is a white dwarf star. White dwarf star's probably about the size of the Earth. All right? White dwarf star about the size of the Earth. Okay? Made almost entirely of iron, which it can't fuse. There is no nuclear fusion after iron. For physics people, you have to go into nuclear fission, which is what we do in power stations with uranium. But fusion stops at iron. You can't fuse iron, or if you do, it doesn't produce any energy for you. Okay? So you can squash iron as much as you like. All right? It's not going to fuse, it's not going to produce any energy for you. About the size of the Earth, so imagine, and the sun hasn't lost any mass. People just think stuff gets thrown out by the sun. It hasn't, it's still got the same number of atoms in it. So tell me about the density of this object. Very, very high. It's the sun, next time you see one of these solar system posters, it's the sun crushed down to the size of the Earth, because gravity's obviously been winning. Okay? Which beggars the obvious question about the white dwarf star. What's the obvious question about a white dwarf star?
Where's the radiation question?
Yeah. In other words, what's holding it up? How strong is the gravity now? Immense. The sun is now the size of the Earth. The gravity is whatever, how many times smaller is the Earth than the sun? Don't know. Oh, it's loads, isn't it? Times 3, because it's in 3 dimensions. So whatever big number you just thought of, cube it. I think it's probably even bigger than that. And that's how many times bigger the gravity is. So the big question with the white dwarf star is what on earth is holding it up? Because there is no fusion. There's a little bit of fusion on the surface, there's a little bit of light given out. They are quite tricky to see because they're quite not particularly bright. But that's the problem, all right? How on earth can they continue when they have stopped nuclear fusion? Gravity is going to be not just still there, gravity is going to be absolutely enormous. And the answer is a new force. Now, in the syllabus, you're meant to know that a white dwarf star is a stage in the life of a star. You're not meant to know how it happens to exist, how it manages to exist, which is a bit daft, really. So let me just explain to you how a white dwarf actually manages. Okay, you won't be asked in the exam to explain this, but common sense, you ought to know what's going on. These stars we can explain with our gravity and radiation pressure seesaw. But for a white dwarf, some new physics happens, basically. The density here is now incredibly high. I'm sure you learnt in year 7 that gold has a density of 19 or something. The density of a white dwarf star is just off the planet. It's like a teaspoon weighs the same as the Himalayas or something bonkers like that. It's just a ridiculous level of density. The sort of density you form in CERN when you smash particles together and stuff like that. An unbelievable density. And when that happens, you're basically at the point where you're trying to squeeze particles into each other. And it produces an outward force called electron pressure. Now, I'm not going to explain electron pressure anymore. It's been a sort of second year undergraduate quantum mechanics. But basically, if you make objects very, very dense, if you make them so dense, like a star crushed to the size of a planet, a small planet at that, if you do that, you produce... Have you ever tried to put 2 north poles together? Now, it isn't magnetism, it's not the same sort of thing, but it's like that. You're right? As you try and push them close together, the 2 particles basically can't be that close for all kinds of quantum physics reasons, and so they push outwards. Okay? With a piece of physics you don't see every day, because matter the size of a star crushed to the size of a planet, we don't come across very often. But this force is called electron pressure, and this is how the white dwarf star happily continues. Okay? This is the seesaw diagram, if you like. Gravity, very, very strong now. Huge gravity. All right, because the sun has been crushed down to this tiny size, but it's stopped by electron pressure. Which of these 2 requires fuel? Neither. So that's how white dwarfs are very, very stable, because they don't require any fuel. The sun has to keep turning hydrogen into helium in order to stay doing what it does. But a white dwarf star is basically there for the duration. We think gradually, this is stage 4, the white dwarf, we think gradually they cool down. They gradually lose their surface temperature and they cool down, and they become, would you like to guess? Not a white dwarf, but a... That's it, black dwarf. Eventually they stop shining. Get it? they become a black dwarf. This process, because there's no, which one's going to give up? Neither of them. Basically, this happens very, very slowly. We believe that some of the first stars in the universe ever to form haven't got there yet. Do you follow? If you look out into space, there are white dwarfs of unimaginable age. They are stars that formed not long after the very first stars ever formed. This process takes an immensely long time. We're not even totally sure about how it happens because it's very hard to see. Obviously, black dwarfs are hard to see, but even the first stars that formed at the first wave of star formation in the universe, even they will only just be heading towards black dwarfness now. So this is not a well understood state in the life of a star. There is a problem though, and it's linked to, I'll leave you to do a bit of research actually. This was basically the theory of stellar evolution for quite a long time, until people started discovering other things. There are supernovae, there are black holes, there are all sorts of strange things in the universe which aren't one of these things. All right? And it was due to a very talented astrophysicist in the early 20th century who had the name, I'm probably going to need to write it down, Mr. Chandrasekhar, Subramanian Chandrasekhar, did a calculation on this. He had a look at this balance. The idea of a white dwarf is a balance between gravity and electron pressure. And about that time, we were starting to understand a bit more about how electron pressure works. Mr. Chandrasekhar did a calculation to do with white dwarf stars, and he found something quite worrying. And that's what we're going to have a look at next time. If you get a moment, you might want to look up the Chandrasekhar limit. What I've shown you here is what the sun's going to do, but probably most stars in the universe will actually have to do something slightly different. All right? And if you were wondering about things like black holes and that, well, there must be another part to the story. This can't be the end of the story. It's for the sun, but it can't be for all stars. And that was the idea of the Chandrasekhar limit, which we'll have a look at next time. Okay?